Okay, so welcome back. So now in this video, we're going to derive or explain why we're going to use this substitution when we have this expression in our integral, okay? And so to start with, let's consider the domain of this function. So if we look at the domain, since it's under the radical, we know that x has to be between or including -1 and 1, okay? And again, we're going to assume that a is positive in this case, okay? So, or excuse me, this is between a and -a, okay? So, we know the domain of this function is from -a to a, so which means that x is greater than -a, greater than or equal to -a, and less than or equal to a. Okay. Now, if we divide everything by a, then what do we get? We get -1 is less than x over a, which is less than or equal to +1. Okay, so we get this expression. Okay, so now, also, let's also realize that sine x, or sine theta, is positive from -1 to 1. Okay. So notice that we have x divided by a is between -1 and 1. We also know that sine, so here's sine, from -1 and 1, right? So notice those two also on the same interval. Okay? So they're on the same interval. And since the range of sine x over this interval, right? So the interval that we're talking about, is for theta. So let's put theta in here. And we're going from -pi/2 to pi/2. Okay. So over this interval, sine theta is from -1 to +1. Over this interval, x over a is between -1 and +1, inclusive. Okay? So, since that's true, then there has to be a unique angle theta. Right? Satisfying this interval. So there has to be a unique angle theta that's in this interval, right? Such that we're between this, which means that gives us x over a is between -1 and +1. So think about it. If theta is between these two, then sine theta is between these two. And so then there has to be a unique angle, theta, such that sine of x over a, right, is equal between -1 and 1. Or that sine of x equals this, right? So there's the connection, right? So if theta is between here, so this is the way we set it up. So let's repeat. So we start with this domain, right? So this is the domain. And we just, using this domain, we came up with this has to be true, right? So this comes from the fact that x has to be between these two. So this inequality says that x over a is between -1 and 1. Now we come over to the integral. So we know that sine theta is between -1 and 1, right, which matches this, when theta is between these two. So that means there has to be a unique angle theta such that sine theta equals x over a. Right? Because x over a and sine theta cover the same interval. So there has to be a unique angle from here to here on this interval such that sine theta equals x over a. That should make sense, right? Okay. So, or equivalently, now what happens? If I multiply both sides by a, look what I get. I get x equals a, oops, a sine theta, right? Now, let's use this as our substitution. Look what we get. Okay, so I'm going to erase this. So now that's why we came up with the x equals sine, or excuse me, a sine theta. Okay, so now let's keep going. And let's do our substitution. Okay, so now if we do our substitution, we get, so here's our substitution. So now we do our substitution into this, and we get the integral. You know what? I'm not even going to do the integral. Just going to do the substitution. So we get, we're going to get, so we have a squared minus a sine theta squared okay. Now watch what happens. Oh, I'll just do this. So now if I do my substitution, I get a squared minus a squared sine squared theta, which then gives me, again, I'm just going through the same process I went through the last video, okay? So now I'm going to factor out the a squared minus sine squared theta, and now I'm going to, oops, let's try this again. There we go. And now, again, I'm going to take now since a is positive, right? And sine squared actually, hold on. I'm gonna go one step further. So a is positive, so I can split this up and take the square root of a. So this just gives me a times 1 minus sine squared theta. Okay, now I'm going to use the Pythagorean identity, and so I get a times the square root of cosine squared theta. Now, cosine squared theta is positive. Okay, so we know that cosine theta is positive, right? So cosine is positive on the open interval. Okay, and so again, we'll deal with the -1 in a moment, but I'll show you how we avoid that. Oh, actually, yeah, we're fine. Oh, hold on. That's not what I want to write. Not -1. I did it here, and then I'm not thinking, so it's 0. Okay, so it's greater than or equal to 0. Okay, so again, we don't have to have the absolute value signs because we'd normally. So at this point, we would say a is a times the absolute value of cosine squared theta. But since cosine is greater than or equal to 0 on the same interval, because it does this, okay? So it's greater than or equal to 0. And so we can drop the absolute value signs, and we get, oops, that's not squared, sorry. The square root of the square here would be the absolute value sign. So we normally always put the absolute value signs when we're dealing with a square root and a square. Okay, so then we can drop those because, like I said, cosine theta is non-negative on the same interval from negative pi over 2 to positive pi over 2. And so we can drop the absolute value and we end up with this result. Okay, which is the same result that we got before in the example in the last video. Now, so we get this. Why? Because a is positive and cosine is non-negative. Cosine theta is non-negative on the same interval. Okay? And that's the result. Okay, so now, so we got the same result that we got before based on our setup. So what we did was, using the substitution, okay, we transformed this expression into a trig, an expression involving trig functions, which we know how to handle. Okay, so after we evaluate the integral, then we can convert back to x, right? So the whole idea of the substitution, right, remember, is to transform something that we can't integrate to something that we can. And then once we do the integration, then we want to go back and put things in terms of the original variable, which in this case is x. Okay, so now once we do that, then we have to substitute back into x. So how do we do that? Okay, well, let's again begin by assuming that x is between 0 and a. Okay, so now we do our substitution, right? We integrate. We're going to end up with a result that has trig functions in it. But we have to go back to x, right? We have to go back to the original variable. So how do we go back to the original variable? Well, first of all, let's assume that x is on 1/2, right? Okay, so if x, again, we're just going to assume it's on from 0 to a. Okay, so it's a positive value. So let's assume x is positive. So that would mean that theta would be what? This is where theta is going to be from 0 to pi over 2, right? So now, so this is the interval that we're looking for theta. So theta is going to be the positive. So now, this is where our right triangle comes in to help us. Okay? And so, since sine theta equals x over a, right? So, sine of theta equals x over a, right? So now what we can do is now we can go over to our right triangle, because again, if we're in this angle, if our angle is in this range, then we're going to be in the positive direction for our right triangle. And so it's going to be opposite over hypotenuse. So remember, the definition of sine theta is opposite over hypotenuse. So that's one of the reasons why we write it this way, so we can see that the opposite is x and our hypotenuse is a. And if you use the Pythagorean theorem, you see that we have to fill in the question mark. And so in this case here, if we say, let's make this, I don't know. Let's just make it a question mark. So we got to figure out what the question mark is. So remember, in this case, it's always, remember, the general form for the Pythagorean theorem is a squared plus b squared equals c squared. Okay, so this is the hypotenuse. Well, in this case, a is the hypotenuse. Okay, a squared plus b squared equals c squared. So it's this side squared times this plus this side squared equals this side squared. Okay, so if we take our question mark squared plus x squared equals a squared, right? Well, if we just subtract x squared, right, we get our question mark squared equals a squared minus x squared. And if we take the square root of both sides, what do we get? We get our question mark equals the square root of a squared minus x squared, which is exactly what we have here. So you can see that our expression becomes one of the sides of our right triangle. So this side has to be a squared minus x squared. Okay. Now, that's going to be the key thing. Okay, so now that we got the right triangle completed, we can see that we can use and we can draw the reference triangle that I have here, and we can assist in expressing any of the values like cosine, tangent, and the remaining trigonometric functions in terms of x, right? So now with this triangle that we just set up, right? So now we've got a way of relating all of the different trig functions that we could get, and we can relate those in terms of trig functions, in terms of x. Now, if theta appears alone, which could happen, then what we would do is we would use inverse functions. Okay? For example, in this case here, if theta happened to come up by itself, then we would basically use inverse, right? So we'd use the fact that theta equals sine inverse of x over a. And so we would use that fact. Okay. Now it can be shown that this actually holds for all theta from negative pi over 2 to positive pi over 2. But I think this is sufficient for our purposes. Okay. So again, that's how we develop the substitution for dealing with this expression in an integral. Okay? So, see you next time.